involving SD and AVM, where we use SD at a low level and within each agent. So let's take a look at this situation here. We've got too many people up here. So let's close this last one off. And let's go to this. Okay, we don't want to see that yet. Okay, so this SD1, this combination of SD and AVM, we're going to have agents, and each agent is going to be associated with a simple distinction between living and dead, so they're in one of those two states. And then they're going to be described, their evolution over time, in addition to being described by that discrete state chart, it's described by a series of stock and flows. And these stocks and flows capture the amount of free virions in their bloods, the amount of circulating virus particles. This shows number of uninfected cells and infected cells. Now we can imagine this, in a specific area of their body, such as their epithelium. Over time, as the number of free virions goes up, the chance rises of a given cell in the epithelium that's been uninfected becoming infected. However, what happens within the body, of course, is there's a regulatory response in the form of the immune system. And in this case, this particular model has a much more aggregate representation of immune response, one that Kurtz worked with and that we formulated in conjunction with an immunologist, a flu immunologist. Is a very detailed model of certain aspects of response to flu infection. That's not shown here. This is, again, a very stylized model. This one is drawn from the literature, though, showing sort of immune response. Immune system stimulated in its cell-mediated immunity capacity, so it's CTL, cytotoxic T lymphocytes. They're stimulated by presentation of antigen and start build up into a stock of activated T cells, I believe, which can go and they can fight the infected cells. So they kill off the infected cells, these activated ones. And there's some immune memory that's built up along with this. We have other versions of this model which have a much more detailed representation of immune memory, which is of strong interest when it comes to things like waning vaccination and waning effects of early exposure to infection, response to an overly hygienic environment. So here we have this stock of T cells of immune cells, and those fight and kill off these infected cells. So within each person, there's this dynamic going on, but betwixt people, we also have some interactions. And you'll notice that up here, there's not only endogenous production of virions with these infected cells undergoing lysis and creating new free virions, but there's moreover, ladies and gentlemen, a buildup of virions from neighbors. And this again is kind of a key nexus within the model. Let's see if I can get it to show it. I thought it was selected there, but there we go. So this this inflow of virions is some coefficient times a function, total virion load from neighbors, and that total virion load from neighbors simply goes and loops over all neighbors and totals up the number of free virions in those neighbors. So it totals up the value of V for those neighbors, and I'll show you that function just so you can see that there's no magic there. So here we go, and you can see here. Now, if only this were written in Scala. And maybe in Java 8 it could be done more compactly. But here we loop over all the neighbors. We deal with the case where there's no neighbors, and we just sum up the total viral load over this. So in short, ladies and gentlemen, we have within this model a situation where we have endogenous dynamics characterized on the one hand by state charts in a discrete fashion, on the other by stock and flow diagrams, and there's coupling between neighbors because each individual is placed into networks. They have a number of connections with other individuals. I had thought here, yes. Come on. There's it's actually, okay, that's kind of interesting that it's sitting down there. I may rue this day, but, okay, yeah, I need to really live in its nice home up here, just to be tidy. So I'm moving this up here. So here we have a representation of the individual in a most stylized form with an oval, and the oval color will be set according to this people color, and people color will evolve according to their virion load, I believe, and I believe the width of this should really be done more nicely now that I look at it. The width of the circle, the radius of the circle is given by Z, Z being the CTL level. In other words, the level of immune cells, activated immune cells. So when we run this, we can switch here, and the infection will start at a certain point here. Let's see where there we go. And you can see it leads to these sort of okay, come on, keep on going. I want to go. You can see it leads to sort of given agents developing high rival load, as indicated by the color, expanding to indicate their immune response. Their immune response puts a damper on the infection in them, so they start shrinking again, but not until they've actually infected their neighbors. So there's this kind of localized breakouts as they've infected neighbors, and you get this kind of boiling phenomena that occurs. The student who was most involved with this, and I think created the first version, Dave Vickers, a very similar version to this, his wife did the boiling model because it had this sort of boiling consistency. So very simple dynamic hypothesis expressed here, very simple idea that if I have high viral load, I'm going to probably leak it to you. And we've examined the impact of changing assumptions here. So suppose it's not spread in continuous fashion, so mine just leaks over to yours, but instead it's spread in a discrete fashion. I'm more likely to infect you with some inoculating dose, some minimum infecting dose, if I have a certain level, higher levels of virions. And the dynamics is very similar. I mean, it's not appreciably different, as I recall. So here they've come down to a certain baseline level of endemic infection. I would note these people over here have very low, I think they're naive and they have very low low infected levels. Now we can set this so that currently all those individuals survive. If we have a medium threshold here of infection, now we can have this, and you'll notice some people start to disappear if their viral load level goes too high. They exit that state chart, and they go into a state where they die. Let's go see that. Let's go back to this person, and this again is one of those things that you capture through a hybrid model. Those differential equations only apply for a certain time. You notice under the condition that their viral load, that's V, goes above a certain viral threshold, then they go and they transition automatically to this dead state. Notice that that's it's beautiful in AnyLogic because it's depending on a dynamic variable v, so it will automatically compute it and make it happen when you cross that threshold. And what happens when they enter that death state is they're removed from the population. So in short, there was survival here. Now this may seem like a curious factoid. They're survived here by only part of the population. This may seem like a curious factoid, having them, or just a little bit cute, but actually it points to a couple things. First of all, it's a powerful thing to have these coupled state charts which can handle discrete occurrences like death together with these differential equations. Secondly, you actually do get some interesting dynamics that well, it would be hard to get that through differential equations alone, but it's moreover a type of situation where you could actually have a transition, say, to situations where other state charts apply. Now other differential equations apply. So I've been involved since this point in building a model, for example, of a pregnancy where, before pregnancy there'd be a mom's metabolism. During pregnancy, the mom and fetus, and then there's two metabolic systems operating, and then following pregnancy they separate, but the mom's system is still affected by the ongoing effects of the pregnancy. And you can actually capture that where they're affected by different sets of stocks and flows, essentially, for different periods of the pregnancy, etc. So it's a very powerful mechanism there. It's moreover one that's subject to a lot of elaboration. It's very easy to add things on in system dynamics fashion. The system dynamics model here, you could say, is aggregate, but it's aggregate at the immune system level. There are people who create more detailed models of the immune system. This is a particularly stylized high level. Okay. Very simple model of how those two can come together with system dynamics within individuals together with state charts. So both dynamic, both continuous and discrete elements. Okay. Different form of hybrid model. One that's, I think, particularly elegant within AnyLogic. So I'm going to stop that here. Oh yes, the other reason I was going to say this is more than just a cute little model. Imagine, these are all fairly homogeneous people, as I recall, but imagine if you really wanted to understand the impacts, for example, of differing immunocompetence. One thing you could do is you could set different people in the population's parameters differently. So, for example, within this model, there are parameters for strength of immune response. For example, this C, right? This value of C, and of course, within the broader population, we have this sets of agents, people here, and we have the option of lending them different values of C. And so here, actually, I stand corrected. We actually did have a model with different values of C. This is like having different people with different strengths of immune systems in the population. Why did some die? Some survive. Those with adverse immune system impact are going to mount a less aggressive response to the incursions of the viral particles. It's going to take their Zs a longer time to build up, and the Ys will be built up more thoroughly, encouraging higher levels of viremia, and therefore they'll be selected out of the population. Does that make sense? In other words, those in this current situation, those with very weak immune systems have a higher chance of death, right? And if we were to go modify this model to account for with statistics for the
So here we go, statistics. Here we go. Mean immune response in the population. Ladies and gentlemen, I already anticipated this, it seems, some years ago. So let's turn on the model time, and now let's run the model in its initial state. And hey, where's that? Where are you? Where's the population? Where's the population? Hey, where is it? Hey, where's this located? I couldn't find it. Where is this? Oh, it's right there. Okay, let's bring it out of there. It gets lost as a stock. This is people. Okay, so sorry, I just couldn't find it to display it. So let's run it.
This looks a lot better on your new computer than your old one.
Thanks. Oh, you know what? Is that invisible? No, it's sorry. It's what am I doing? Okay, this is I'm at the no. This is main. Okay. Okay. Oh, it's the wrong model. Maybe you're right. Is it the wrong model? Wait. Okay. Hello. No, it's the right.
You don't see that whole class.
Yeah, it's. Oh, okay. So let's. Oh, I see. It's a different view of it. Okay. Well, within AnyLogic, you could set it to have different areas of the screen to view, or different regions to view. So I think we were at this statistics table. There we go. Okay. So early on, that is it's reporting some information there. Come on. Oh, why won't you let me click on you?
Can you click on the other ones?
Well, these guys are just stocks, but I wanted to actually see the statistics, darn it. Okay, this is imported from AnyLogic 7, and I'm wondering if it's got a ghost in the machine. Okay, so why won't this, hello, why won't it let me click on it? Okay, visible, yes, okay, yeah. Oh well, I was going to go display what the mean level was of the mean immune response. And what we would have seen, I believe, is that essentially early on it would have been, I think that, no, that's the mean viral load there. But in any case, okay, here, what we'll do is we'll solve the problem in the most direct, straightforward mechanism. Okay, so let's go, and we don't need this to be nearly so big. Boom. And we don't need it so big from up here either. And let's move this out of the way. Let's go create a graph of it. Okay, and let us go to the palette, and we'll drag in from the analysis side, we'll drag in a time plot, and this will give us the mean viral, the mean value of C, of immune system response strength. So in a way, it's related to immunocompetence. Okay, we're going to add a data item, immunocompetence, and its value will be people dot, and oh come on, you won't do autocomplete. Okay, so what is it called? It's called people dot what? Mean immune responsiveness. Okay, good. So now let's go back to this. Boom. And we'll do mean immune responsiveness. Great. Okay, there we go. And this will be mean immune responsiveness. Great. Okay, so I think we should be good now to go. Okay, now, here we go. And as the infection spreads, you notice what's happening. Can anyone interpret that for me? Let's watch that again. Okay, as the infection spreads, what's this doing? Mean immune responsiveness.
People are getting accustomed to it.
Well,
People that have low
yeah,
are dying off.
are dying off, So there's a natural selection occurring to people with lower levels of immune responsiveness. So people with stronger immune systems are mounting a more effective response. That obviously depends on the threshold for dying off. If you have this threshold, we have essentially very few people, being so adversely affected that they disappear. Okay, so this is a little hybrid model, right? Okay. Okay, so I'm going to stop the recording on that. We'll go on to